Imagine a skyscraper swaying during a magnitude 7 earthquake and remaining fully intact. At the same time, the occupants continue their daily routines, unaware that the building's movements are all part of an engineered response to seismic activity. Following devastating earthquakes in Japan and California, engineering codes have been revised to incorporate structural systems such as base isolation, energy dissipation devices, and geotechnical innovations. In Tokyo and Los Angeles, modern skyscrapers like Taipei 101 and the Wilshire Grand Center demonstrate how new construction methods help tall buildings withstand intense ground motion. These advancements are based on decades of global research and seismic testing. This paper explores how tall buildings are designed to resist earthquakes by integrating isolation systems, energy absorbing technologies, ductile structural frameworks, and advanced foundation techniques that minimize damage and maximize safety. To begin with, base isolation technology can make medium-rise masonry or reinforced concrete structures capable of withstanding earthquakes, protecting both structures and their occupants from major damage or injury. Seismic dampers further help control the seismic energy that buildings are supposed to during ground motion. The combination of these systems result in significantly reduced building movement and stress. Research has shown that when base isolation and tuned mass dampers are used together, seismic energy can be reduced by over 80% compared to structures without them. For example, Taipei 101 in Taiwan uses a 660-ton tuned mass damper which can reduce swaying by up to 40% during an earthquake or typhoon. These systems do not stop earthquakes but rather reduce the force transmitted to the structure, acting as a cushion between the building and the shaking ground. Thus, base isolation and damping technologies work together to reduce sway and prevent structural failure during strong seismic events.
Furthermore, the buckling restraint brace or BRB is a composite structural member designed to carry axial loads without buckling even under large deformations. Buildings must be able to bend without breaking during major earthquakes. The use of BRBs allows buildings to deform significantly without losing strength, making them ideal for high seismic zones. For example, the Salesforce Tower in San Francisco employs a belt truss and a trigger system that enhances the building's lateral flexibility while anchoring the central core. Research shows that structures with multiple load paths and well-designed plastic hinge zones recover fast post-earthquake and remain functional. By designing buildings that can flex and absorb energy, engineers ensure that tall structures can survive even intense seismic events. In addition, geotechnical engineering and foundation design are crucial to how tall buildings handle seismic forces. Local soil conditions can amplify ground shaking, requiring tailored foundation strategies. In areas with soft soil, such as Mexico City, engineers employ deep foundations such as piles and mat foundations to anchor buildings into stable ground layers. Soil stabilization techniques like jet grouting and soil compaction are also used to prevent liquefaction, which can cause buildings to tilt or collapse during an earthquake. Moreover, soil structure interaction models allow for more precise foundation design, reducing the risk of lateral movement during earthquakes. These strategies ensure greater safety and performance of tall buildings in seismically active regions. Overall, tall buildings are engineered to withstand earthquakes using isolation systems, energy dissipation devices, flexible structural frameworks, and soil-specific foundation strategies. These innovations keep modern skyscrapers safe and functional during seismic events. As research advances, future designs may integrate smart sensors, adaptive materials, and AI-driven monitoring systems that make buildings more even resilient. By adopting earthquake-proof technologies worldwide, cities can not only safeguard lives but also ensure that urban skylines remain symbols of strength and security in an era of increasing seismic risks.